In this section, we present a new concept which allows us to use functions to study curves which, plotted in an xy plane, neither represent y as a function of x nor x as a function of y. Let's take this xy coordinate system and pretend that a small ladybug is crawling on my computer screen. So the bug lands here. And then the ladybug decides to walk in this direction. Then she says, well, I'm going to turn around and then I'm going to go this way and then perhaps take off. We know that this curve that the ladybug has sketched out does not represent y as a function of x because it fails the vertical line test. And it does not represent x as a function of y because it fails the horizontal line test. So we can't call this a function as is, but what we can do is that since the bug, or the ladybug, can be in only one place at any given time t, we can define the x-coordinate of p as a function of time, and we can define y as a function of time. So here, let's say time is 0, that's where the ladybug landed. She has an x-coordinate of about 5 and a y-coordinate of 1. Then she walked along her path, and let's say time is 1 second here. X is about 4 and y is about 2. And we could keep walking up, and let's say here 2 seconds have passed. Her x-coordinate is about 3, the y-coordinate is about 4. So we could plot the points. It's not a function of x or y. What we have is that the point, or the places that the ladybug is traveling, is a function of t, or in this case time. The independent variable t in this case is called a parameter, and we get a system of equations to sketch out a curve. So what we're going to be looking at today is looking at those system of what's called parametric equations, where we have a different type of parameter. Most of the time it's t for time, other times it could be angles or whatever. And as we look at this parameter, we also will notice that the curve has a certain orientation, meaning it has a beginning and possibly an end. So it travels in this direction, and we note that by putting little arrows. Not just an arrow at the end like we've done before to say it goes to infinity and beyond. It's more of a direction. So our goal today is to take a set of parametric equations, and we're going to learn how to sketch the curve, we're going to indicate that orientation, and then we're going to eliminate the parameter to get an equation involving just x and y and compare those two graphs. So how are we going to sketch the curve? The easiest thing to do is plot points, but we have an x, a y, and a t. So let's make a table of values where t is our independent variable, and then we have x and y, and then we'll plot it on an xy coordinate system. That part's very important. That's your parameter. It says that t can only go from -2 to 3. So let's start with -2. You always want to start with the lowest values and go up to 3, and just plot these points and then connect the dot. So the first thing I'm going to do is use x. Alright, so x is -2 squared minus 3. And keep going in like manner. Do 0. Put in 1. Put in 2. And then 3. And we should get those values for x. Now we're going to put those same t values in for y. Right? So we have y equals 2 times -2 minus 1. Then we have y equals 2 times -1 minus 1. And then keep going. Now it's time to plot these points on our XY coordinate system. Alright, so we're going to plot 1, -5 just like you've done forever. And this is when t equals -2. I'm doing that so I know the orientation, since the lowest value of t is -2. Then I'm going to plot the next point. And again, this is when t is -1. And then I want to connect those dots in a smooth curve as possible. I don't put an arrow at the end because t stops at 3. So that's it. I do need to show its orientation, so I could do that by plotting the little t values here. But go ahead and put little arrows to say the curve was swept out from its beginning to its end. So I've done everything except eliminate that parameter. How can I do that? Well, we're just going to use the substitution. So let's look at those two values and let's solve for t in one of them and substitute it back into the other. Well, if I take y equals 2t minus 1, I think that'll be a lot easier to solve for t than this one, because here, in order to solve for t, I'd have to take a plus or minus square root. That just is ugly. So let's come over here and solve for t. So I'm going to add 1 and then divide by 2, and that's t. And then I'm going to substitute it into the other equation. And you don't have to go any further, but look at that equation. We just studied conic sections. Is that not a parabola? The y value is squared. It should be a parabola going to the side. But notice here, our parametric equation, we only got a portion of the parabola. What would the whole parabola look like? Using the computer, I've graphed the whole function, and you can see that this is a parabola on its side, and we would go on indefinitely where our parametric function stops at the beginning and end. Now, it doesn't always do that, but because our t values were very limited from -2 to 3, we only get a portion of that whole parabola. Let's do the second one. Right, so we want to graph it, indicate its orientation, and then eliminate the parameter. You do not have to do it in any particular order. I like to graph it first. Again, my independent variable t, and then x, and then y. Okay, so look at here. T can be the smallest of 0 and then keep going. So I could just randomly pick some numbers greater than 0, that's okay. But let's rewrite x. What does that 3/2 power mean? That means the square root of t cubed. And here we have y equals the square root of t. So it might be convenient when I'm picking my values of t to pick nice things I can take the square root of. Or you can pick up your calculator. But let's see, I'm going to start out at 0 and then 1, 4, 9. I think that'll give me an okay idea. Alright, so x equals the square root of 0 cubed plus 1. X equals the square root of 1 cubed plus 1. X equals the square root of 4 cubed plus 1. So that's 2 cubed, that's 8 plus 1, that's 9. And then we have the square root of 9 cubed plus 1, that's going to be 28. Might have to fudge that a bit on my graph. So for y, I just need to take the square root of my t values. So the square root of 0, the square root of 1, the square root of 4, the square root of 9. So again, these are the values I'm going to plot on my xy coordinate system. Right, so 1, 0, and that's when t is equal to 0. 2, 1, and then 9, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, up to, and that's when t is equal to 4. So we've progressed in this progression, and then if I go way out here, dot, 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 up to 28, it's going to get a little bit up to 3, but it's going to keep going. It's going to keep going because t keeps going. So I want to indicate the orientation by saying, yes, it went in that direction. When you're picking your t values, you always want to go from small to big. Now let's eliminate that parameter. If I go back to here, square root of t is already solved for, and I can just plug that back in here, right? So I have x equal, and in place of the square root of t, I can put y. So I have y cubed plus 1. Good enough. Perhaps you may remember what that cubic function, or actually, you don't have to do this, but if I subtracted 1 and then I took the cube root, you may remember what that cube root function looks like. So with the magic of the computer, I've kind of rearranged some things. Again, this is fine for your answer as far as eliminating the parameter and getting an equation with just x and y. You can leave it like that, but look at this graph compared to this one. You can tell we only got half of that graph, again, because of the parameter t was only greater than 0. What happens when we have sine and cosine? A little bit different. So let's just approach it one step at a time. Look at our values of t. If you want to change that to 180 degrees, that's fine. Again, I'm going to make my chart. And so I want from 0 to 180 degrees. Well, I know those would be easy. What about in the middle? I could choose 30, 45, 60. I could choose all of them. I think I'm just going to choose 45 degrees and 135. That's pretty much right in the middle. All right, so again, I have x equals 2 times the cosine of 0 degrees. What is that? That's 2. X equals 2 times the cosine of 45 degrees. 45 degrees is square root of 2 over 2 times 2. What's the cosine of 90 degrees? That's right. It's 0. And then 135 is negative square root of 2 over 2, so I'm going to get this value. And the cosine of 180 degrees is negative 1 times that 2. So those are my x values. Yes, I might need to get a calculator to kind of approximate to be able to graph it. Now what about y? Y equals 3 times the sine of 0 degrees. The sine of 0 is 0. And then 45 degrees, remember, is square root of 2 over 2, so this is 3 square root of 2 over 2. The sine of 90 degrees is 1 times 3 is 3, and keep going. I'm going to get those values. So again, I want to graph those on my xy coordinate system. Well, let's first just graph the ones I can graph. So I know 2, 0, 0, 1, 2, 3. Right? Remember, this is when t is 0. This is t equals 90. I'm going to call that pi over 2. And then I came down here at 180, or pi. So I'm definitely going around in that direction. If I get out a calculator, plot those points, let's see. It's going to be somewhere about right there. And remember, this doesn't keep going. Very limited. What does that look like? Anything familiar? Let's get there. So let's take this and eliminate the parameter. Well, if I solve for t, I would get something like this. Inverse cosine of x over 2. That is just ugly. Do not do that. Well, let's see if sine gets any better. If I divide by 3, no, I would have to take the inverse sine, and that's just as ugly. Let's not do that. Let's come back up to here. How could I put those together and get rid of the cosine and the sine? Use the Pythagorean identity that relates cosine squared and sine squared. Well, I have cosine, I just need to square it. So I'd have x over 2 squared. The sine is y over 3, I just need to square it. Look at there. What if I write that a little bit better? X squared over 4 plus y squared over 9 equals to 1. What is that? That is an ellipse with the center at 0, 0. You would go out 2 on the x-axis and 3 on the y-axis. So because of the parameter, I only get half the ellipse rotating in a counterclockwise direction. And that's the equation that eliminates the parameter. And if you wanted to see the whole ellipse, what would it look like? And if you were to graph the whole ellipse, that's what you would get. But remember, the parametric equations only gave us that top half. I have a challenge. Do a little bit of research of what the cycloid is and be ready to discuss that in class.